In this video, we will cover the remaining topics from Unit 1. Here you can see the topics covered in this video. First, we have combinatorial optimization. Then we will try to understand different types of combinatorial optimization problems using example. Multimodel optimization problem using example. We have single variable, multivariable optimization. It is further categorized as constraint and unconstrained optimization. So we have single and multivariable constraint and unconstrained optimization, and in the end we will try to understand one multivariable constraint optimization problem using particle swarm optimization algorithm. So first we have combinatorial optimization problems that we will try to understand using examples. Multimodel optimization, then we have single and multivariable optimization based on constrained and unconstrained. Then in the end, using particle swarm optimization, we will solve one multivariable unconstrained optimization problem. So first we have combinatorial optimization. It is the process of finding either minima or maxima of any objective function. So this process involves find out the best solution from a finite set of possible solution, and we can represent the solution either in the form of combinations or arrangements of the elements. Here you can see different types of combinatorial optimization problems: traveling salesman problem, knapsack problem, graph coloring problem, and job scheduling problem. In the traveling salesman problem, we have a salesman that want to visit a set of cities and return to the start city. So the goal is to here find out the shortest possible route that cover minimum distance. So here you can see we have input set of cities. For simplicity, suppose we have 4 cities A, B, C and D. Then we have distance between each pair of cities. You can see distance from A to B 10, B to C 35, C to D that is 30, A to D that is 20, and so on. So the goal is to find out the optimal order in which the salesman visit the cities and then return to the start city, and the total distance should be minimum. Here you can see we have possible routes. We have n possible ways salesman can go from city to city, and so we can find out different possible routes for the salesman. For example, it can go A to B, B to C, C to D, D to A, and this route cover 95 unit distance. Like that we have n ways. For example, A to C, C to D, D to B, B to A, or A to D, D to C, C to B, then B to A. So we have n ways. Now for example, you can see for this route we have total distance covered that is 80 unit, and for this one 95 unit. For example, suppose this route is the optimal solution as it covers the minimum distance. So like that we have n ways we can find out the routes for the solutions, but the question is we have to select the optimal route that cover the minimum distance. So we have a number of approaches that we can use to solve this problem. For example, we can use exact methods. In exact methods, we have brute force, dynamic programming, integer programming, heuristic methods. Then we have meta-heuristic optimization. So we can use any method and it will give us the possible solution, and we can find out the optimal one. Another problem, we have a knapsack problem. In the knapsack problem, we have given a set of items. Here we have set of item A, B, C, D and E, and each item you can see we have weight and a value, and in each item you can see we have weight and value associated with it. For example, for item A, weight is 2 unit, value is $7, and you can see for each item we have given weight and value, and we have given a knapsack. The knapsack capacity is 10 units. So determine the number of each item to include in collection, and total weight should be either less than or equal to then the given limit, and total value is maximized. So the goal is here to determine the maximum value that we can obtain by selecting best combination of the items without exceeding the weight capacity of the knapsack. For the knapsack, we have given weight capacity is 10 unit. Now suppose now we will add the items into the knapsack. First we added item D. Weight we have 1 unit, value 5. Now we have 1 unit added in the knapsack. Remaining capacity left 10 minus 1, that is 9. In total value we have 5. Next we added item E. For this weight we have 4 unit and value 8. So now remaining capacity for this we have 9 minus 4, 5. Total value is, in this value we will add 8. Next we added item B. So we here for item B weight is 3 unit. Now the remaining capacity we have 2 and total value is 17. Last we added item A. Weight we have 2 unit. Now remaining knapsack capacity is now 0. So total value we obtain 24. So here for this problem the optimal selection is to take item D, E, B and A. So you can see item C is not taken and total value we got here 25. So like that we can form a number of combination for the items using these methods. Either we can use exact method, heuristics or meta-heuristics. They will give you the optimal solution after a number of iterations. And in graph coloring problem we assign the color to the vertices of graph so that no two adjacent vertices having the same color. And in job scheduling problems, tasks are assigned to the resources over time to optimize given objective. Here objective can be either minimize the completion time or maximize the resource utilization. You can use any method to solve these problems. Next we have multimodel optimization that refer to the optimization of multiple models simultaneously. For example, suppose we are working on computer vision system for object detection and this system contain several networks for image preprocessing, feature extraction and object detection, and all these networks are working all together in a pipeline, and each network has its own hyperparameters, configuration and architecture, and that can influence the overall accuracy of the system. So the goal is to optimize the entire system for best object detection accuracy, and it involves finding the best combination of these parameters across 3 networks. Parameters you can see here. For image preprocessing network, we have image types, data intensity. In feature extraction network, we have number of layers, filter size, learning rate. Object detection network, we have anchor box sizes and detection accuracy. So we have to optimize all 3 networks simultaneously in order to find out the best object detection accuracy. And you can see here different methods that we can use to solve these problems. It involves evolutionary algorithms, swarm intelligence, or we can use hybrid models that we discussed in part 1. Next we have single variable optimization. In single variable optimization we have to minimize or maximize the value of a function, and here it's subject to just one single variable. For example, we have this function and we have to minimize the value of this function. We can use different techniques, gradient based method, evolutionary algorithm or machine learning based approaches. In gradient based method, we initialize with a starting point and then this point iteratively update until convergence, or we can use evolutionary algorithm or machine learning approaches. So we have just one single variable here. Next you can see here optimization problems are further categorized as constrained and unconstrained optimization. So first we have single variable unconstrained optimization. For example, this problem, it is unconstrained optimization problem. We have no constraint given here, so it is a unconstrained optimization problem. Next we have multivariable unconstrained optimization problem. In multivariable optimization problem, again we have to either find out the minimum or maximum value of the given objective function, but here we have multiple variables. Suppose we have given this objective function and here we have 2 variables x and y. We have to find out the minimum value for this objective function. We can use different techniques, gradient based method with multiple variables, evolutionary algorithms, PSO algorithm, machine learning based approaches. Next we have single variable constraint optimization. Here we have to either find out minimum maximum value for any objective function, but here it's subject to a constraint. The final value should satisfy the given constraint. Value of x either should be greater than or equal to 2. Then we can say, only then we can say the solution is the optimal solution. We can use different techniques to solve single variable constraint optimization. For example, constraint optimization technique like Lagrange multipliers, evolutionary algorithms with constraints. Then we have multivariable constraint optimization. Here you can see we have multiple variable x and y. Then it's subject to a constraint. Solution should satisfy the constraint. Only after that we can say it is the optimal solution. So here you can see this is the objective function and it's subject to a constraint, that is x plus y should be greater than or equal to 1. We can use certain techniques, constraint optimization method like nonlinear programming, sequential quadratic programming, genetic algorithm with constraints, or interior point methods. So here you can see our optimization problem. Goal is to minimize the Rosenbrock's banana function and it's subject to certain constraints. We can use certain methods. You can use different methods to solve this problem. Interior point method, KKT, SQP, penalty function. So we are using here particle swarm optimization algorithm. We have given this function and we want to minimize this function and it's subject to constraint, that is x plus y minus 2. It should be less than or equal to 0. So you can see the pseudocode for the particle swarm optimization algorithm. First we will define the objective function, that is here this one. This is the objective function. Then we will initialize the position for each particle, evaluate their performance using the objective function, select personal best and the global best value. Then we will start the main loop for this algorithm. We will calculate the velocity and then update the new position for the agents, then update, then evaluate new solution, update local and global best, repeat the process until stopping condition is met. Now we will initialize the population. Suppose we have two particles P1 and P2. For the simplicity, it is multivariable optimization problem. So for P1 position we have x1, y1. For P2 position is x2, y2. Initialize the position and the velocity. Suppose the position for the first particle P1 is 0.5, 0.5, x1 is 0.5, y1 is 0.5. Position for the second particle we have x2, 1.2, y2 minus 1.2, and the velocity we will consider 0 initially. And after that, so here you can see the position for the first particle, it is 0.5, 0.5. Position for the second particle, it is 1.2 and minus 1.2. Now we will calculate the fitness value for each particle. Here we will put these values in this objective function to find out the fitness value. For the first particle, x we have 0.5, y we have 0.5. Put the value and we got the fitness value for the first particle 18.5. Same for the first part, same for the second particle. X we have 1.2, then it is y we have minus 1.2. Put the values here. Again it is x2, then y2. Put the value and we got thickness value, that is 697. Now we will update their personal best. Personal best is their own fitness value. So here you can see their personal best. For the first particle it is 18.5. For the second particle it is 695. Now we will update the global best. Global best means the best among all. So here we have just two particles. So the best value among two is the first particle, that is 18.5. Next we will update the velocity and the position for each particle. So suppose the weight and inertia value we have 0.5. Coefficient C1, C2, it is 2.0. Then the random value we need here, you can see in the equation we have rand. We have two random values. We have R1, R2, R1 0.3, R2 0.7. Calculate the velocity for the first particle. So here we have multiple variables. So we will calculate for both x1 and y1. So here put the value here, w we have 0.5 initially velocity for particle we have 0, then we have 2 into r1 we have 0.3. so put all the values and we got the velocity for the first particle 0. Now update particle position, it is same. So the first particle position is still same, there is no change. Now we will do for the second particle. Here for the second particle you can see, so here we have 1.2 comma minus 1.2, put the values here, and the global best value we have 0.5, you can see, and we got the for point x2 minus 0.98, for y2 3.1. now we calculate the velocity for both points. So here now we will update the position for the both point, so we can update position by adding the velocity in the previous position. So in the previous position 1.2 we added the value that we calculated here, that is minus 0.98, so it is 0.22. for second point it is 1.9. so the new position for this particle is updated, that is 0.22 and 19. Now we will evaluate new solutions. So first we will check the constraint violation for the new position, if this position satisfies the constraints or not. So here you can see for the first particle position is 0.5, 0.5. Put the value here, 0.5 plus 0.5 minus 2. This time for this particle constraint is already satisfied. This particle position is updated. Put values here in this constraint, 0.22 plus 1.9 minus 2. We obtain a value that is 0.12. And according to the constraint, values should be less than or equal to 0. So here the constraint is not satisfied. In optimization problems, if the constraint is not satisfied, then we cannot consider the solution as the feasible solution. Now we can use different approaches to solve this problem. We can use penalty method, repair mechanism, we can have constraint handling techniques, hybrid approaches. If you want to use penalty method, you can use this. Here you have to penalize the objective function with constraint. So here in penalty method you have to penalize the objective function when constraints are violated. So in penalty method a penalty term is added in the objective function. You can see here this is the objective function and we added here penalty term, and you can see the penalty term is this one. Further the value for lambda is 100. Either we can use the penalty method. This is the most common method used. So this time we will use here second approach, that is the repair mechanism. So here we will set the value for y to the maximum allowed value. So value for x is, you can see, so value for x is 0.22. If we will consider this value, then y is equal to 2 minus x. You can see, put the value for x, that is this one. So new value for y we got here 1.78. So new position, that is the adjusted value for the second particle, it is now 0.22 and 1.78. Now you can add the values in this function, 0.22 plus 1.78 minus 2. This time the constraint is satisfied, so we can calculate the fitness value for this particle, and here we obtain the new fitness value for the second particle, that is 300.14. Next we will compare the solution. So when you will compare the solution, we will compare the new solution with the older solutions. In this case for the first particle it is same, there is no change. For the second particle you can see the position, older position is this one, the new position is this one. Now we will compare the older solution with the new solutions. Here you can see we have two particles, older position and fitness, two particles, new position and fitness. For the first particle you can see it is same, there is no change. For the second particle you can see the position is updated. Now when we are updating the particles personal best, we will consider the best. For example here for the first particle it is same, no change, we will consider this. For the second particle, when we will consider the personal best fitness value, you can see for the second particle it is 697, for the second particle it is 300. So new one, the new value we obtain, it is matter, so we'll consider this. So for the second particle we will consider this new position as the, so we will consider this value as the best value. Now when we will update the global best, then we will select the best among all. Right now still here for the first particle fitness value, it is minimum, then this particle, so we'll consider this as the global best for the first iteration. Then we will repeat the steps until suppose if you have maximum iteration 500, repeat the loop until 500 iterations, then the whatever solutions you obtained in the last iteration, display that solution as the best solution. So like that we can use different techniques to solve multivariable optimization problems. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.